All right, let's get started. So the topic for today's lecture, there's actually going to be two parts. I'm going to first talk about asynchronous and parallel algorithms, and then we're going to take a little break, and then I'll talk about some open problems and challenges in deep reinforcement learning. This is actually going to be the last lecture that I'm going to give, then Chelsea's going to have one more lecture, and then we're going to have guest lectures for the remainder of the course while you work on your final projects. So quick overview of sort of some of the stuff that's happened so far. So so far in this class, we learned about a number of policy search methods: model-free algorithms, model-based algorithms, policy gradient algorithms, Q-learning algorithms, all that stuff. And so far, we've learned about all these algorithms as kind of sequential algorithms, where you kind of conventionally have a sequence of operations, you execute it, and everything is good. But is there actually a natural way to parallelize reinforcement learning algorithms? So it turns out that the answer is yes. In fact, there are many different ways that we can think about parallelizing reinforcement learning algorithms for efficiency, both efficiency in terms of wall clock time and efficiency in terms of sample complexity. So you can parallelize the sampling of the experience, you can parallelize the learning process, you can have multiple learning threads, multiple experience collection threads, and so on, and that's what I'll talk about today. So in today's lecture, I'm going to first give you kind of a high-level schematic of what a generic reinforcement learning algorithm looks like. And then I'll talk about how each of those pieces in that generic reinforcement learning algorithms might be parallelized, and then dig down into specifics of particular algorithms that have been proposed in the literature that try to parallelize those parts. So we'll talk about a number of specific RL algorithms, and then we'll talk about some of their trade-offs and some considerations when thinking about asynchrony and parallelism. So the goals for today, for this part of the lecture, will be to understand the high-level anatomy of a reinforcement learning algorithm in a very generic way, understand standard strategies that we can use for parallelization, and the trade-offs of different parallel methods. And just before I get into this, just a reminder that for your final projects, your project groups are due today, so be sure to send a note to berkeleydeeprlcourse@gmail.com with your group members and your project title. Please don't send any questions to that address. If you have any questions for course staff, post it on Piazza, because we don't actually check that regularly. It's just for assignments. But do send your title and group members tonight. OK, so let's start with kind of a very generic look at what an RL algorithm looks like. For the purpose of today's lecture, I'm going to say that an RL algorithm really consists of three parts. It actually doesn't matter whether it's a model-based RL algorithm, model-free RL algorithm, a Q-learning, policy gradient. They all have the following three parts. They're going to have some way to generate samples, which typically amounts to running your policy either in a simulator or in the real world, but just some way to generate those samples. They're going to have some component that fits a model or estimates a return, and I'll explain in a second what that means. And they're going to have some component that's going to actually use that model or estimate of the return to improve your policy. And then this process repeats. And I'm going to try to keep the color coding consistent for today's lecture. So orange means generating samples, green means fitting some kind of model, and blue means improving your policy. So fitting the model could mean a number of different things. So if you have a model-based RL algorithm, fitting the model could literally mean fitting the model, estimating the probability of seeing the next state given a current state in action. If you have a policy gradient algorithm, this step actually becomes kind of trivially degenerate. It might just mean estimating the total return by summing over the rewards that you saw. So this is not really like computationally very demanding. It just means add together a bunch of numbers. But it's still a kind of model. It's a prediction. If you take this action in this state, what's the return you're going to get? Well, a very simple prediction is just to sum up the returns that you actually saw. So that's what policy gradient does when you don't use a value function estimator. And then if you're doing something like an actor-critic algorithm or Q-learning, this could mean, for example, fitting a neural net to the Q function. So all these things are models in the sense that they make predictions about the future. So these are not in themselves policies. They're just predictors for something that will happen next if you take a particular action in a particular state. And all RL algorithms have some kind of model. Just in the case of algorithms like policy gradient, that model might be trivially simple, just consists of adding together a bunch of numbers. And then improving the policy, that's where you actually try to compute a new policy that makes things better. So in the case of model-based RL, this might actually involve optimizing your policy by propagating gradients through your model. And there are a lot of kind of nuances to that, as we covered in the beginning of the course. If we're doing policy gradient, this is where you'd actually do your gradient step. And if you're doing Q-learning, this step might just be trivial. It just might amount to saying, well, my policy should be the argmax of my Q function estimator. So for Q learning, there might be nothing to do here, but for actor critic, this is where you would actually use your parameterized Q function to improve your policy. So in some cases, one or the other of these modules is trivially simple, but in many cases, there's some interesting computation going on in each one. OK, does this schematic make sense to everybody? Does anyone have any questions about it? OK. All right, so which parts of this diagram are problematic? Which parts are slow? Well, the obvious one that we can start with is the generation of the samples. So if we're trying to run reinforcement learning on a real robot or a real car or a real power grid, whatever system you'd like to control, this part is limited to 1x real time until we can invent time travel. So this is kind of likely to be a big bottleneck, because for real world systems, time moves forward at 1x real time. In simulation, this becomes a lot less of an issue. So for something like the Mujoko simulator that you used in homework 1, well, the Mujoko simulator in a good implementation can actually run it up to 10,000x real time. So this is likely not to be a huge bottleneck. Although in a bad implementation, it can run much slower than that. So in simulation, this maybe is less of a concern. But with simulation, there might be a concern with data locality. So even if parallelizing the sampling is not really the main thing you want to do, you might still want to parallelize the sampling just so that if you have multiple workers in different machines, they're all generating their own samples without having to shuffle the data around. So I'll get into that a little bit. But typically, the main kind of situation where parallelizing the sampling is important is if we have the real systems. OK, fitting a model or estimating the return. So as I mentioned before, for things like policy gradient, fitting the model is trivial, so there's not really much to do there. But if you want to fit let's say, a neural net Q function like you did in homework 3, well, this part is actually kind of expensive. And it's actually non-trivial to parallelize because you're going to be running stochastic gradient descent, and parallelizing stochastic gradient descent, there are a few kind of nuances that you have to consider. But that's a good candidate for parallelization. With improving the policy, the opposite story. If you're doing Q learning, this part is trivial. There's pretty much nothing to do there. But if you're, let's say, doing a model-based policy optimization, then this might be a really expensive step. And there you might also consider doing something with parallel SGD, for instance. All right, so which parts can we parallelize? So we can parallelize the generation of samples. If we have real systems, this could be as simple as just we have multiple physical systems or whatever kind of real system you have, multiple instances of it, maybe in different situations, all collecting data and pooling it into a common replay buffer. But it could also mean that if we have, let's say, a simulated setting, we might have a separate instance of the simulator running in every thread or on every machine in a parallel setup. The model fitting, so here a lot of the methods that we use for parallelism resemble kind of classical methods for parallelizing SGD, and I'll talk a little bit about that. And same thing for the policy fitting. So the stuff over here is going to look a lot like parallel SGD, and the stuff over here is going to look like some version of run multiple data collection threads and pool all their data into one giant replay buffer. But there's quite a bit of nuance in how you actually do this. And one thing to consider at a very high level about when it comes to parallelizing our algorithms is that it really helps to group data generation and training. So if you have a worker that's generating data, whether it's running a simulator or whether it's attached to a physical system, it's often a good idea for that same worker to then do a little bit of additional stuff, like compute some gradients or something like that, and then send the gradients over instead of sending all the data, because typically if we're doing deep RL, we have fairly high bandwidth data, and if we actually process the data locally and only send around gradients or something even simpler than that, we can have some pretty nice savings in terms of bandwidth. All right. So let's talk about some high-level decisions when it comes to devising your parallel RL algorithms. So one decision that's going to pretty strongly affect what your algorithm looks like is whether it's an online or a batch mode algorithm. And the other one is whether it's a synchronous or asynchronous algorithm. And you can have different combinations of these. So the first one really depends on the particular algorithm that you're using. Online means that you're going to modify your policy or your model every single time step. Batch mode means you're going to collect many, many samples and then modify your policy. And both of those could be either synchronous or asynchronous. So synchronous means that it might be parallel, but the different steps wait for each other, and asynchronous means that they don't. So here's a diagram of how we might parallelize a policy gradient algorithm. So when I draw these diagrams in this lecture, when I have a green bar like this, that means the synchronization point. So that means that everything to the left of that green bar is going to wait until they all finish, get synchronized here, and then move on to the stuff to the right. So this is a very generic kind of drawing of a policy gradient algorithm. Now, we all learned about policy gradient algorithms. Can any of you guys tell me whether policy gradient algorithms are online or batch mode in general? The Monte Carlo kind, not the kind with value function estimation. So online means that every single time step you update your model or policy, and batch mode means you collect a bunch of samples and then do a big improvement step. Yes?
It's batch mode, right?
Correct, yeah. So policy gradient methods are batch mode because you end up, especially if you're doing Monte Carlo returns, if you're not using a value function estimator, because that gradient estimator tends to be pretty high variance. So one of the simplest ways to combat that variance is to get many samples, average them all together, and get a good gradient estimate. So policy gradient methods typically tend to be batch mode. Actor-critic methods can become online, but standard policy gradient is batch mode. And can somebody tell me whether this diagram is illustrating a synchronous or asynchronous algorithm? Synchronous, right. So even though it's parallel, it's synchronous because you're collecting all these samples, waiting for all the experience collection to finish, pooling them all together, and then doing a policy gradient step. And in fact, this is the most trivial kind of parallelization you can do for policy gradient because all of that experience collection doesn't have any mutual dependency, so it's trivially parallelizable. When you actually go to apply that gradient to the model, there you need to do something a little more clever. And if you just put a standard kind of hard synchronization here, this is mathematically identical to standard policy gradient. So this stuff can be parallelized without any change to any of the underlying theory. So this you can always do with policy gradient. If you want to remove the synchronization, then it gets a little more nuanced. Here's another diagram for a funny little Q-learning version of a deep RL algorithms. So in a Q-learning setup, this now is going to be an online algorithm because in Q-learning you actually would modify your model, your Q function every single time step. And you can implement this as either a synchronous or asynchronous algorithm. So the way I have it drawn here, it's actually synchronous because you're going to generate one step of experience, use that one step of experience to compute gradients, pool those gradients, synchronize the model, and then take another step. But you could also imagine thinking through what happens when you remove this synchronization point and just let all these threads run in parallel asynchronously, pooling their parameter values sort of on the fly. That gives you an algorithm with slightly different mathematical properties. It's not going to be mathematically equivalent, but turns out to still work if done right. And I'll actually cover a version of this later on in the lecture. OK, does anybody have any questions about these two high-level decisions, whether your algorithm is online or batch mode, and whether it's synchronous or asynchronous? All right. So at this point, it's perhaps a good idea for me to mention a little bit about parallel stochastic gradient descent. So in this lecture, I'm talking specifically about how we can parallelize reinforcement learning algorithms. But the question of how we parallelize reinforcement learning algorithms is very closely related to the question of how we parallelize stochastic gradient descent. So typically when we're training a deep neural network model with, let's say, supervised learning, we're using stochastic gradient descent. And we can actually parallelize stochastic gradient descent. And there are a few ways to do it. And it's a good idea to understand some of the trade-offs. I'm not going to go too deeply into the theory here, or I'm actually not going to go into the theory at all. But I just want to give you a high-level idea of what's going on here. So when you're parallelizing the model or the critic or the actor, typically this involves parallelizing a stochastic gradient descent procedure. The simplest way to parallelize stochastic gradient descent, this is from a paper on parallel stochastic gradient descent by Dye et al., is to have a collection of workers where each worker has a different slice of the data. So that's what's represented by these green icons here. So you have a big data set. You slice that data set into parts. Each worker gets a part of the data set. Each worker is going to compute some gradients on its own part of the data set, sum those gradients together, and then send them to a parameter server. So there's a single parameter server that keeps sort of the canonical version of the model parameters. And that parameter server is going to sum those gradients from all the workers and send back new parameters. Now, what you can do is you could actually ask this parameter server to synchronize everything for you. You can just say, all the workers are going to send me their gradients every iteration, and I'm not going to let them continue until I've summed up all of their gradients and send back fresh model parameters. That's mathematically equivalent to standard SGD. So whether these are different machines or one machine, at that point it's equivalent. If you don't want the parameter server to wait, if you want it to basically just add in the gradient that was just sent to you, send back the model parameters, and let that worker run, even if the other workers haven't yet completed this iteration. That becomes asynchronous stochastic gradient descent. It's much quicker because you don't have to incur the communication delays, and if one of your workers is slow, you don't have to get slowed down by that. But at that point, it is not mathematically equivalent to standard SGD because different workers are going to have different versions of the model parameters. So the reason it's not equivalent, just to be clear, is that this worker over here might send me some updated gradients. I might change my model parameters. And then this guy who's still crunching on this data with old model parameters might send me his gradient. And I apply that gradient, but now that's not actually the gradient of my new model parameters. So that turns out to not be mathematically equivalent to standard SGD. Under some assumptions, you can actually show that this converges to something sensible. But in practice, it's a little tricky. Sometimes it actually makes things better. Sometimes it makes them worse. Yes?
How much can that be thought of as like essentially like reducing the batch size for just a regular standard gradient descent?
The asynchronous version?
Yeah.
It's not quite the same as reducing the batch size because it's not like, so yeah, each of these guys has some batch size. The trouble is not the batch size, it's actually the fact that if I apply a gradient from worker number 1, now I have some value of my model parameters. Worker number 2, in the meantime, is trying to compute gradients for an older version of the model parameters. So by the time he sends me his gradients, those are gradients, but they're gradients at a different point, evaluated at a different point of the model parameters. So that's where some of the complexity happens. There's still a bunch of theory you can do that I won't get into this lecture to try to understand what happens there under some assumptions about basically how old things are, how convex things are, and so on. But it gets a lot more complicated. So asynchronous SGD typically doesn't achieve perfect parallelism, but the lack of locks, the lack of the synchronization can make it actually a lot faster in practice. And how well it works tends to be somewhat problem dependent. All right, so that's kind of a very, very high level discussion of parallelized SGD. So now let me start going through a few examples of ways that we can actually parallelize reinforcement learning algorithms, and I'll kind of work my way up to some algorithms that are actually used in practice. So first, let's talk about policy gradient. And here we'll go back to that picture I showed before, but I just want to walk through it in a bit more detail to make sure that we're all on the same page. So first what I'll do is I'll show you sort of a step-by-step schematic of a policy gradient algorithm just to make sure that we're all on the same page with that. So if you're doing policy gradient, step 1 is going to be to collect a bunch of samples. So each of your samples is a trajectory, so it's a sequence of states and actions, S1A1 through STAT, and you collect that by running your current policy pi theta, and you run it n times to get n trajectories. Then you're going to compute the reward of each trajectory. So this is just a little notational shorthand, but when I write r of tau, that's really the sum over t of r of STAT. So you're going to compute the rewards of all of your samples. Then you're going to compute the gradient for each of your samples. And this maybe looks a little bit different than what John covered because I specifically want to decompose the gradient over samples because it'll make it very convenient later. But what this is saying is that this is the sum of the grad log pi, and this is the reward minus a baseline. You can also do a gradient estimator that's decomposed in time the way that John discussed, but I just want to use the simple one here where it's treating the whole trajectory as one sample. So this is the grad log probability of the trajectory, and this is its reward minus a baseline. So standard kind of vanilla policy gradient without any fancy tricks. And then step 4 is you update your parameters by adding your step size times the sum over all of your samples of the gradient of that sample. Okay? So very simple kind of vanilla policy gradient, but just written here explicitly decomposed over samples. So that step 3 is doing a per sample computation, and step 4 is doing a reduction over all the n samples. And I'm writing it this way specifically because it'll make it easier to describe the parallel version. So the really, really simple version of parallelized policy gradient that I showed before, if I had to number these by saying which step this is just step 1, and over here we have step 2, 3, and 4. So in step 1, I collect all the samples in parallel, I put my crossbar here, and then over here I apply steps 2, 3, and 4, and I get an updated vector of policy parameters. So that's all good. Now, could somebody tell me how I could do a little bit better? If I want to exploit parallelism a little bit more, which step can I perhaps move from over here to over here? 2 and 3, yeah. So let's start with the easy one. Let's start with 2. So 2 is trivially per sample. So the computation done in step 2 in the same way that step 1 trivially parallelizes over samples, step 2 absolutely trivially parallelizes over samples. In fact, some people, when they write down these RL algorithms, they actually assume that the reward just comes out during the sampling process, which is also a reasonable way to treat it. So you can just evaluate the reward in parallel with all your samples. The more nuanced thing is that step 3 over here, step 3 is also per sample. So there's nothing in step 3 that actually involves any dependencies between the samples except for the model parameters. So if your model parameters are synchronized over here, then you can compute all the gradients in parallel. Now this is actually potentially quite important because computing, even if evaluating the reward is trivial, computing the gradients very likely is non-trivial, especially if you have a deep convolutional neural network model where the backpropagation takes a lot of time. So the fact that we can parallelize these gradients over here, this might actually be very beneficial. And then all we have to do in step 4 here, the step that's shared, is just sum up those gradients. So summing up those gradients is very cheap. It's just O of n, where n is the number of parameters, times m, where the number of samples. Is there a question?
Yeah, so does this require that you copy the model parameters like back and forth? You have to have like a neural net on each machine, right?
Yeah. So this is what the synchronization point represents.
I see.
So here, the gradients from all of these guys arrive. We wait for all of them to come in, then we apply them, and then we send them back. I guess I'm missing sort of the circle that comes around, but we send them back out to all the workers.
Is that part like slow? The fact that you have to like, if the neural net's very big, does that require a lot of memory?
Well, it depends on what you're doing. So parallelism might mean different things. Parallelism might just mean that you have multiple threads running in the same process on the same machine, in which case it's not a big deal. I mean, it's likely just sitting in shared memory. If you're talking about some massive thing where you have a data center and these things are running over the network, then that's a different story. And I'll talk a little bit more about that too. But in general, the bandwidth, so the model parameters, I mean, what's the size of model parameters? On a bad day, it's maybe in the millions. On a good day for something like a tower game, it's substantially less than that. So if you compare that to the size of like images, like if you have a trajectory where your observations are images, that's going to be way higher bandwidth. So just the fact that the sample generation and the consumption of those samples here is happening in the same thread, that already massively reduces the amount of bandwidth that you need. But yeah, so this guy, in a fully synchronous version, this guy would have to send the gradients back, or the model parameters back out to the workers. So this is still synchronous, but it's parallel, yes?
The baseline can also be parallelized, right?
Yeah, so I haven't talked at all about the baseline, but that's also an interesting story. And with baselines, I'm going to talk about actor-critic algorithms later on, and the way the critic works and the way the baseline works is very similar. So the other thing about this little schematic of a parallel policy gradient algorithm is that it looks pretty much exactly identical to parallelized SGD with synchronization. So in the same way that parallelized SGD with synchronization is mathematically identical to standard SGD, this is mathematically identical to standard policy gradient, if you have this green thing over here. OK. Any questions about parallel policy gradient? OK. Yeah, and that's the parallel SGD. OK, so now what if we add a critic? So let's now rewrite this algorithm to make it an actor-critic algorithm. So to remind you, policy gradient, you just use your Monte Carlo sum of returns. Actor-critic, you're going to replace that sum of returns with some function approximator. And there's different ways to do it, and John covered a number of different ways to do it. In his lecture, I'm going to present one way, but actually the way that you do the parallelism is going to be the same in all the cases, so don't worry too much about it. So steps 1 and 2 are the same. Collect your trajectories, compute your reward. But now in step 3, we're going to actually estimate our critic, which I'm going to use an advantage critic here, and John covered this in his lecture a little bit. You can use a Q function critic, you can use whatever. I'm just going to use A to denote an advantage critic. But this is whatever kind of critic you want. And you're going to update your critic basically by regressing to some kind of target value. And there are a number of different choices in how you compute the target value. You can use a Monte Carlo sum, you can use bootstrap to say it's current reward plus next critic. Lots of different choices. The same kind of high-level system diagram in every case. So see John's lecture if you want to know about specific choices for step 3. And then in step 4, I'm going to compute, again, a per-sample gradient. And now my per-sample gradient, it looks exactly the same, except that here, instead of R minus B, I have my critic. And there, you can have a baseline there, too, all that stuff. But for the sake of simplicity, I'm going to say it's multiplied by my critic. OK? So it's standard actor-critic gradient. And then step 5, is the reduction. Sum together all the gradients and update the model parameters. All right. So I can, of course, parallelize the sampling and the rewards. That's all good. So this is my step 1 and 2. I'm going to generate samples and compute rewards. Then each of these workers can compute their own critic gradients, so they can use whatever samples they have going on in there to compute some gradients of their own critic. Those gradients can then be synchronized, and I can apply the gradients to the critic. So this is all step 3. All right, so far so good. Now I also need to compute a policy gradient for each of these samples. That can still be parallelized, but in order to compute these policy gradients, I need to know the critic parameters. So I need to send this critic in here, which means that these steps have a dependency on these steps finishing first. Okay, that's getting a little nasty. And then I synchronize again, because now I need to reduce these gradients down to a single vector of model parameters. Now this is still equivalent to the fully serial version of the actor critic algorithm, but now it has 2 points of synchronization, and it's getting kind of ugly and messy to write, and even messier to draw. So this thing here is kind of maybe annoying to us, because we have this stuff and we need to wait, and then we need to do more computation in each thread before we can continue. So what can we do? Well, we can just remove it and just sort of hope for the best. And that's actually not such a bad idea, because this critic, your critic is not going to be perfect anyway until you've really gotten to the point where you've solved the task. So if your critic is not perfect anyway, the fact that it's one iteration behind potentially might not be such a bad deal, so long as it's roughly pointing you in the right direction, your policy gradients over here are still an improvement direction. So if your critic is going to be messed up anyway, maybe it's okay if it's a little bit old, and maybe the additional gain that you get from being able to run faster and not having to wait for that synchronization point might be worth the trouble. All right, so before I move on to the online version, does anybody have any questions about the parallel, now asynchronous actor critic algorithm? OK. And this is no longer mathematically equivalent to the serial version of actor critic, but there's a reasonable argument for why this is OK to do, and you're not going to incur a very heavy price for it. All right, so now what if we want this actor critic algorithm to run online? So instead of batch mode, where each of these worker threads collects a bunch of trajectories, pools them together, and then performs the gradient updates, what if we wanted to update the critic and the actor as it's going? Well, turns out the change is actually very simple. There's no change to the diagram at all. All I've changed is I set up here, instead of collecting an entire trajectory, just collect a sample, s, a, s prime, by running the policy for one step, compute the reward of that sample, update your actor, maybe with one gradient step, and then update your policy with one gradient step on that sample, and then pool your gradients. Very simple change, and now we've just switched from batch mode to an online algorithm. So now we have an online asynchronous actor critic algorithm where we have critic updates. They get sent off to the parameter server, which and from that parameter server, we pull the critic values, which might be old values. Yes?
So in, I think 2 slides before, you could also have removed the green line, no?
Yes. And then I would get, in the same way that this thing was synchronous parallel SGD, if I remove the green line, I get asynchronous parallel SGD.
And you would need the regression for the advantage.
Yeah, so here you can remove the green line and not have a critic. That's perfectly fine too. I just didn't want to talk about it too much because I'm not aware of any results from people who have done this, so I can't tell you how bad it is. I don't want to tell you something if it might be unboundedly bad. Okay. I think it would probably work, but I'm not aware of anyone who's tried it. OK, so now that I've described this online asynchronous actor critic algorithm, I can tell you about an algorithm that's actually used in practice, which is an algorithm called A3C, which stands for asynchronous advantage actor critic, which is just an instantiation of that generic algorithm I had on the previous slide, where they make particular choices for a hat. So they're using an advantage estimator for a hat. They share parameters between the policy and the critic. And the update here, instead of being performed every single step, is actually performed every n steps. So they accumulate gradients for a few steps, single-digit number of steps, and then they send them off to the parameter server. So just to be clear how the asynchrony works in this algorithm, if we were to visualize the different threads, the different worker threads that are shown here in blue, so here this is like the progress of time. most of their time they spend, this blue region, they spend computing gradients or sampling. And then when they get to this green thing, that's step 5. So here, they're going to send off their gradients to the parameter server. The parameter server is going to update the model, send back the updated parameters, and this guy's going to keep running. Now, in the meantime, these other two guys, until they've reached their own gradient application kind of point, they're still using old parameters. So then, now the second thread over here, for this little region, it's using old parameters. Now it sends off its gradients and gets back new parameters. And the same with that third thread. So at any given time, your workers are typically using somewhat older parameters, but not too old, because they're going to synchronize with a parameter server every n steps. OK, does this part I think is kind of important to understand, but does everybody understand this? Yes?
How do you gather the gradients to give them back the updates?
So this thread is going to send gradients. The parameter server is going to add those gradients to the parameters, and it's going to send back the parameter vector.
So if the second thread send in some gradient, do they average the first two gradients, or do they?
It's just applied as it arrives. So you can think of this guy as having a very, very, very simple job. When somebody sends a gradients, it adds those gradients to the parameters and sends back parameters.
So all these threads are different copies?
Slightly different, yeah. So this is just like in asynchronous parallel SGD. Yes?
So it's like sending a gradient and then it's immediately getting an updated gradient, or it's waiting, it's going to get it only after?
Right, so this part, this little green thing, it is going to wait. But it's not going to wait for the other threads. It's only going to wait for the parameter server. So it's going to send the parameter server the gradients, and then it's going to get back the parameters. Now, in reality, there's ways to optimize this, because this guy knows which parameters it was using. But this guy over here would not, because he might actually have an old parameter vector here. So if he just applies his own gradient to his parameter vector, that's not the same as waiting for the parameter server to send back the updated parameters. So in general, if you have multiple threads, you do have to wait for the parameter server to send you back something. You could optimize it by not waiting and just starting to run and getting the new parameters as soon as they're ready. But that gets a little wacky. And to my knowledge, most A3C implementations don't do this. They do actually wait for the parameter server, but not for the other workers. Yes?
So when you say collect sample for one step, you literally mean roll out one step and then do all those operations?
Well, with the caveat that the step 5 is only done every n steps.
I see.
So in reality, this blue region, this is actually n steps.
Oh, okay.
And the reason for that, there's two reasons. One is that you don't want to incur the communication overhead too much. And the other one is that you don't want like one sample worth of gradient to shove the parameters in some weird direction. So you want to accumulate a little bit. Any other questions?
So how is it different from just updating the model in its own thread?
Oh, because, so imagine this thread, thread number 1, send gradients. Now the parameters theta in the parameter server are different from the ones in thread 2. Right? So thread 2 has old parameters. So now if thread 2 were to simply apply its own gradients to its own parameters, it wouldn't have the same parameter vector as what's in the parameter server. So it needs to send its gradients to the parameter server, let the parameter server perform the gradient descent, and send back the new values. Because that's the only way that this thread is going to get the contribution from this thread to the parameters.
But the gradient would not be accurate for the server.
Right, it would be a little bit old. Yes, a little bit. OK, so some differences between kind of synchronous actor-critic or Q-learning algorithms and A3C. So typically implementations of typically but not always, implementations of A3C don't use a replay buffer and instead rely on the diversity of samples from different workers. So if you remember John's discussion about replay buffers, a big part of the reason for it is to decorrelate the samples, because if you're constantly taking the sample that's online, they're going to be correlated in time. So you can use a replay buffer to decorrelate them, but if you have multiple workers, that also acts to decorrelate them. Now, in reality, it's still kind of like a little touch and go, like it tends to be not super stable, but seems to be OK in many cases, yes.
So I guess we kind of assume that by tuning the batch size, we want all the gradients from the single threads to be approximately equal, right? So we don't have them drift off. So is there an advantage to just, if we just had one thread and we just applied the same gradient twice, instead of having two different
Well, if you had one thread and you apply the same gradient twice, that's more or less what momentum does. And typically, when you're optimizing model parameters with this, like I have this drawn as like vanilla gradient descent, but you do something a little fancier like momentum or atom, which does something a little bit like that. Now, that said, just blindly applying the same gradient many, many times is not such a good idea, obviously, because it's evaluated at the wrong parameter value.
It seems to me that it is, if we assume that the expectation of the gradient is the same because we have a sufficiently large batch size, it seems to me that once the different threads are out of sync, that's exactly what we're doing.
But they're not out of sync too much. Yeah. So I guess you said apply it twice,
Yeah, apply it
which is okay. If you apply it like 50 times, then you might be in trouble. So it is important for them to synchronize like pretty regularly. So if one of them decides to go to sleep and wait for 3 hours, you probably want to do something careful there. Okay. Now another big difference between this method and serial implementations of Q-learning is that there's some variability in exploration between the workers. So the fact that they have slightly different parameter vectors might be seen as a bad thing, and sort of mathematically it's kind of a bad thing because it doesn't quite make sense. But it can actually be a good thing for exploration because they're all going to execute slightly different behaviors. And in fact, a common practice is to actually further kind of accentuate this difference by giving the different workers slightly different exploration strategies, either different amounts of noise, different values of epsilon for epsilon greedy, to further kind of take advantage of the fact that they have diverse exploration strategies. One big advantage of this kind of approach is that it tends to be much faster in terms of wall clock time. So if you do have enough compute resources to run multiple threads, you'll probably finish faster in terms of total wall clock time. Although typically these algorithms are slower in terms of the total number of samples. And I'll talk more about sample complexity later on in the lecture. All right, so that's A3C. Now, to kind of show you a little bit about the trade-offs with this algorithm, these are some plots from the original A3C paper on Atari games. The yellow line, and just as an advice in your homework, please don't plot your result in a yellow line. It's really hard to see. But here the yellow line is their algorithm, and they're kind of making the point that it's faster, but it's also in many cases better at exploration just by virtue of having these multiple workers and achieves a better score. So that's kind of the good news. The bad news is made a little bit more apparent from a comparison to some other algorithms. So this is a follow-up paper that actually attempts to improve the sample efficiency of A3C. And this is a Mujoko cheetah task. And this is actually 20 million steps right here. And you can see the algorithm converges after about 80 million steps. If you compare this to a serial implementation of DDPG, the serial implementation of DDPG, this is 1 million steps. And the cheetah pretty much converges after 100,000 steps. So the price you pay in sample efficiency is actually enormous, even if in terms of wall clock time, you can end up being faster. So that's something to consider, that with enough threads, faster in terms of wall clock time, but likely multiple orders of magnitude slower in terms of sample efficiency. OK, yeah, more on this later. Now, we can also parallelize model-based algorithms. So here I'm going to tell you a little bit about some work on parallelizing guided policy search, which is a model-based algorithm. So again, let me go through the schematic of guided policy search. Not too different from the other stuff. You generate a bunch of samples by running your policy. Now, if we're going to use these, if you remember from early on in the class, we're going to use these fitted local linear models. So we have multiple samples from each initial state. So the initial states are S0J here. We're going to fit local models for each initial state, use LQR to get updated local policies, and then update the global policy, the neural net policy, by imitating these local policies. So that was the imitation of optimal control lecture in the beginning of the course. So the standard sort of serial version of guided policy search looks like this. You generate your rollouts, you update the local models, update the local policies, run this imitation learning procedure to get your neural net, and then repeat the process. And just like before, we can parallelize this. We can parallelize the generation of the samples. We can parallelize the fitting of the dynamics, the updates to the local policies, and the imitation learning. So here's kind of a system diagram of how this might work. We're going to have local workers, what we're going to call local workers and global workers. So the local workers are going to be per initial state. So per each initial state, there's one local worker that's going to generate rollouts, fit dynamics to those rollouts, update the local policies, and also store that data in a replay memory. And then separately, a bunch of global workers are going to pull samples out of this replay memory and train the neural net. Now, in reality, when you actually go and implement this, it's awfully convenient if you have this on multiple machines to have one local worker and one global worker running on each machine, because then this global worker can just pull from the replay memory on that same machine in shared memory and just send back gradients to a parameter server. So with the same kind of philosophy as earlier in the lecture, the data gets to stay in the same place, and it's just gradients that are going to get passed around. And that's a very efficient way to implement something like this. So in reality, the way you might do this on a physical system is that this pair of local workers and global workers might be actually like physically attached to an actual robot, and this is somewhere on the network. There's a parameter server that's pooling the gradients for the neural net. So this is an illustration of that method in action. Here there's 4 robots, and the robots are literally physically attached to a computer in the back, and that computer is running 2 processes, a local worker that's actually running the robots, fitting dynamics, and updating the local policies. The dynamics fitting and the local policy updates are very fast, so those are just serial with the experience collection. And then there's a separate process running on those machines in parallel, asynchronously, that is then grabbing that memory and updating the neural net. So this is the kind of parallelized asynchronous guided policy search here with 4 workers. So does anyone have any questions about this process? Let me go back to the diagram. OK, great. And then here's another example of a parallelized algorithm for model-free, in this case, deep reinforcement learning. But unlike A3C, this one is actually optimized more for sample efficiency than for wall clock time. So this is using something called parallel NAF, which stands for normalized advantage functions. You can think of NAF as basically Q-learning for continuous tasks. So in Q-learning, you're learning this Q function. In homework 3, your Q function actually outputs a different value for every action. With continuous actions, you have infinitely many actions, so you can't output a different value for each one. But what you can do is you can represent your advantage in some convenient form, like being quadratic in the action. So if it's quadratic in the action and you're just outputting the parameters of that quadratic, then maximizing it is easy. So here the neural net actually outputs 3 values: mu, which is the linear term in the quadratic, p, which is the matrix, and v, which is the scalar field for the value function. So it's kind of a continuous Q-learning algorithm. And then again, there's going to be multiple workers. And the layout of the system is going to be this, that there's going to be a different worker for each experience collection thread. There's going to be a single worker for actually training the Q function. So the Q function training is not actually parallelized. And there's a shared replay buffer. So all the workers are just contributing to the replay buffer. Asynchronously, the training thread is pulling from that replay buffer and updating the Q function. And as soon as it updates the Q function, sends the latest parameters out to each of the workers. This is a very simple algorithm to parallelize because Q-learning is already off policy. So it's OK if the workers are running slightly old parameter vectors. The algorithm actually doesn't care. And that turns out to actually work reasonably well for some real-world robot tasks. So here there's 2 workers, and they're learning to open this door. And this is about 2.5 hours of real-world experience. OK. Any questions about parallelized NAF? OK. And then you can kind of take this idea to the extreme, and you can have an enormous number of workers. So this is an example of an extremely trivial reinforcement learning algorithm, but running on many, many different workers. So there's 14 robots. They're all collecting experience. The actual reinforcement learning algorithm under the hood is very, very simple. It's actually an instance of a bandit algorithm, which is something that John covered in the last lecture. So there's actually no temporal component to the decisions. So that, of course, leads to trivial parallelism, where you collect your samples, put them all in a big bucket, and then completely offline, like someone else pulls from that big bucket and updates their model. So anyway, point is that you can have this stuff range from really complicated, elaborate synchronization stuff to really simple things with an emphasis on quantity. All right. So that's it for asynchronous and parallel algorithms. We're going to take a short break, maybe 3 minutes. If you guys have any questions to ask, please do. And then after the break, I'll talk about challenges and open problems.
actually just wondering, so for parallelizing stuff for SGD, it's like, I think by now very well understood that you can almost do anything and it still works.
Yep.
Like, you can throw out all the locks and stuff. So for methods like policy grading, does all that hold true, at least if you work in like the very simple setting where you have like sort of tabular or like linearly parameterized policies? Is that very well understood?
Let me think about that. I'm not aware of any work on it. I would imagine that a lot of the same ideas as in asynchronous SGD still apply, because in the end, policy gradient is just estimating the gradient of some function. It's an unbiased estimate of the gradient. So insofar as the results for asynchronous SGD apply for unbiased gradient estimates, they should still apply here.
Yeah.
But I don't know that for sure.
Okay.
I'm like 90% sure of that.
Okay, but for things like, for example, like Q learning is actually like fundamentally different
Yes.
than like just like optimizing some fixed objective.
Mhm.
Has there? I mean, I guess people in practice can like sort of try to parallelize Q learning in whatever way they might in practice. But is it understood like if you did some sort of parallelized variant of Q learning? Or whatever?
Well, so there's some analysis of this in the A3C paper.
I see.
They do look at parallelized SARSA, I think, which is
Okay.
kind of like Q learning. But I'm not aware of like really solid theoretical results on it.
Okay.
But solid theoretical results with Q learning with nonlinear function approximators are going to be tough anyway.
Oh, yeah.
For
I
the
mean, not for
for the same reasons that John covered.
Yeah.
For tabular,
Or
I'm not sure, but I also haven't looked. So there might be something that I'm just not aware of.
Okay, interesting. Okay,
Mm-hmm.
thanks.
Are there any experiments where they've scaled to like millions of agents and this parallelization types of?
Not sure. I would imagine that past a certain point you get diminishing returns because sort of for the same reason that using enormous batch sizes is not super helpful. I'm not sure in fact, how far people have scaled like A3C style algorithms. The most, like the simplest way to do it is just run multiple threads on the same machine, which gets you some number, but not like millions.
Yeah, thousands.
Yeah.
Okay. Quick question: Are there any office hours for any of the instructors next week?
Next week is spring break, so we don't have any class.
Question for asynchronous SGD, when you have gradients from old parameters, what if you think of that as some sort of like momentum?
Yeah. Well, so actually, this is in response to the other guy's question too. Is that some of the theory for why like asynchronous SGD works actually like resembles a little bit some of the arguments about why momentum works. So there's they're closely related ideas. The deeper theory of that is probably outside the scope of this class, which is a polite way of me saying I didn't read about it before doing this lecture. But there's definitely a lot of theoretical work on that.
Oh yeah, that's right. It's so narrow.
Yes.
In John's lecture for SVG, he had an expectation on the outside and on the inside. But then like a couple slides later, he took out the outer expectation.
Maybe come to office hours about that. I'd have to think a little more carefully about what's going on. All right, so I'm going to continue, and actually the second half of the course of the lecture today is going to be on something completely different. So I'm going to talk about challenges in deep reinforcement learning, and this is kind of meant to set the theme a little bit for your final projects. So if you're thinking about final projects, I figure this might be a good time to tell you about some of the bad news when it comes to deep reinforcement learning. Basically, what are the things that are hard? What are the things that we don't know how to do? And what are the big outstanding challenges? So I'm going to give you a high-level summary of deep RL challenges. I'm going to talk about stability, sample complexity, and scaling up and generalization. And then I'll say a little bit about reward specification very briefly at the end. So the goals will be to understand the open problems in deep RL, understand the trade-offs between different algorithms in a little bit more detail, and hopefully give you some ideas for what you might want to think about for your final projects. So to get started, sort of by way of motivation, let me tell you very quickly about some works in deep RL. This is not necessarily the most important works, but just a few examples of kind of research papers in this field that have done something, that have enabled some kind of capability, and a little bit about what about those papers actually made them enable that capability. So these papers, I think, are all ones that we've covered previously in the class. So this is the work by Lang et al. On reinforcement learning from raw visual inputs. This was covered in one of Chelsea's lectures. Guided policy search, which I talked about. Q learning with deep Q networks, which John talked about. Trust region policy optimization, which John also talked about. Using guided policy search for vision-based tasks. actor-critic algorithms like DDPG, AlphaGo, which is actually a combination of supervised learning and reinforcement learning. This paper, this I actually didn't cover, but this was a kind of a large-scale reinforcement learning project for robotic grasping. So with these works, one of the things, you can think of this as a somewhat biased random sampling. The interesting thing to note is that the new capability that was enabled in each of these works can neatly fit into one of three themes: improving the stability of deep reinforcement learning algorithms, improving their efficiency, and scaling them up. So the work of Lang et al. Really, you can look at it as an improvement of stability. So you could choose to learn a Q function directly from images, but if you embed that Q function in a low-dimensional space, then you can use a really nice, simple RL algorithm, and it's going to be a lot more stable. With guided policy search, really there the emphasis is on getting model-based algorithms to work, so it's really on efficiency. Yes?
What do you mean by stability?
Stability in the sense that you don't have to spend hours, days, or months tweaking hyperparameters. With deep Q networks, I would argue that actually a big part of why this work succeeded where others had failed was actually the additional improvements that they introduced for improving stability. Things like the replay buffer, which allows the decorrelation of the samples in time, and target networks. So really, if you think of the difference between this and just a naive implementation of Q learning on top of convnets, the main difference is the stability of the algorithm. And the same with trust region policy optimization, that by formulating a trust region on the parameters rather than using vanilla gradient descent, the big improvement is that it's a lot easier to choose the right parameters to make the algorithm actually work. This, again, is a model-based method, so the emphasis on efficiency. With DDPG, really a big improvement there over the policy gradient methods was the much more efficient learning that's enabled by introducing a critic. With AlphaGo, I think it's probably not a controversial point that a big ingredient for its success is the large-scale evaluation of massive numbers of self-play games, as well as a huge amount of supervised learning data for initialization, and the same with the grasping work. So these three components, stability in regard to convergence properties, sensitivity to hyperparameters, and so on, efficiency, meaning the number of samples that you need to actually learn an effective policy, and scale, meaning can you actually throw lots of very diverse and varied data at the algorithm and have it actually learn to perform effectively and robustly under varied conditions. And these are the three things that I'm going to talk about. So let's start with stability and hyperparameters. Now this is going to be a very kind of practical and empirical discussion. There's a whole other side to this as far as the theoretical properties of when it comes to stability and convergence, but I'm going to actually focus more on the kind of the practical aspect of this. So devising stable RL algorithms is very, very hard. And some of you might have gotten a preview of this in homework 3 if you, for example, implemented things a little bit differently than we expected. You tried to run them, even if your implementation was mostly correct. You might have gotten lousy performance because the hyperparameters weren't quite right. So the hyperparameters we gave you were really designed for a particular standard implementation of Q learning, which is what most of you did. But even a small change, like, for example, not using a sum reduction rather than a mean reduction for the error, might change the effective behavior of the algorithm dramatically. So when it comes to things like Q learning and value function estimation, of course, fitted Q and fitted value methods with deep network functions are not typically contractions, which means there's not any guarantee on convergence, and this is what John discussed in his lecture. But practically, that means that the hyperparameter tuning is what's going to make it actually work. So because in general it won't converge, it's sort of up to you to tweak it and tune it until it does. And there are a lot of parameters that are very important for stability. Things like the delay for updating the target network, the size of the replay buffer, how you're clipping your gradients, the learning rates that you're choosing, if you're using a more advanced optimizer like Atom or Momentum, how you're choosing the parameters of that optimizer. So these are all end up being actually quite important and quite non-trivial to set if you want to apply one of these algorithms to a new problem setting. When it comes to policy gradient methods or likelihood ratio methods or reinforce, now you do actually get you can actually get guarantees of convergence with these methods, but you have a very high variance gradient estimator, and in practice you have to play all sorts of games to get the variance of that estimator down to something manageable so that you can actually get those favorable convergence properties with a finite number of samples. Typically, there's different ways to solve it, some more appealing than others. You can just use more samples, you can devise more complex baselines, and do all this stuff. And important parameters to think about are things like the size of the batch, the learning rate, and the design of the baseline, or control variant. And then with model-based algorithms, there we're not really in the clear either, because even though the main component of a model-based algorithm looks a lot like supervised learning, the fitting of the model, the particular model class matters a lot. And unlike with kind of large-scale supervised learning where you have a giant data set and just use the biggest neural net that'll do the job, with model-based RL you have to consider what's going to happen early on in the learning process when you have very little data, and you can overfit catastrophically. So choosing the model class is very important. You can go with a very simple model class like local linear models, or a really complex class like neural nets, and they have different trade-offs. And then even if you get a good model, actually optimizing your policy with respect to that model is itself highly non-trivial because it involves this enormous backpropagation through time problem. And as I discussed earlier on in the class, there's all sorts of tricks that we can take to kind of get around that. So here we're not necessarily in the clear either. OK, so what should we do? What should we think about when we're going to tune our hyperparameters? Well, one of the first things to do is to get used to it, at least with algorithms that we have today. So get used to running multiple hyperparameters, and especially if you're devising novel algorithms, it would be a really good idea to get used to running hyperparameter sweeps, because it would be really sad to devise a really great algorithm and not realize that it's great because you didn't choose the right hyperparameters. So one technique that's very appealing if you're devising new methods and you're working in simulation is to get used to the idea of always running with slightly different settings for the hyperparameters that you know are the most sensitive. So for example, you might set up your script so that you can specify a range of hyperparameters and automatically kick off jobs that run all the different combinations. But you start getting into trouble once you have more than one or two of these hyperparameters. So you can think of, OK, we're going to specify little arrays for every hyperparameter and run all of the different combinations. So it's a grid-like layout. But that gets really impractical in higher dimensions. So if you have more than two hyperparameters, actually random selection of your parameters when you're doing a hyperparameter sweep is much, much more effective. And it's actually the only viable option in much higher dimensions. And let me give you an illustration for why. This is somewhat shamelessly stolen from some slides from Yoshua Bengio, but I think it's a very good illustration of this idea. So let's say that you have two hyperparameters, and one of these hyperparameters really matters, and the other one doesn't. So that's what this little terrains at the top and the side are illustrating. So this hyperparameter is unimportant, so the return doesn't change much. That's the yellow curve here. This hyperparameter is very important, so the return changes drastically. Now, if you use a grid layout and you, let's say, run 9 different training runs, you've just wasted two-thirds of them because this unimportant parameter is going to produce the same return regardless of what you set it to. So you've only gotten 3 samples for that important parameter. If instead you randomly choose your hyperparameter settings for the same 9 runs, now you have much denser sampling of this important hyperparameter, and you can figure out that it's really this value that you should pick because that's the one that produces a really good return, whereas over here you'll miss it completely. So remember that even though it's very convenient to set up kind of these grid sweeps, if you have more than 1 or 2 hyperparameters, it's really much, much better to run the random search. And don't forget about the random seed, too, because a lot of these algorithms are going to be very sensitive to their initial conditions. And there's a very good reason for that, is that reinforcement learning is kind of self-reinforcing. So for a lot of these algorithms, especially if the exploration strategy is not super sophisticated, as soon as they discover a successful strategy, they'll keep reinforcing that first successful strategy. And if that first successful strategy is sort of arbitrarily chosen from a bunch of different options, different runs of the same algorithm might produce very different results. Changing the different hyperparameters might therefore change the performance of the algorithm more than it actually should, because it's just sort of arbitrarily changing the randomization a little bit. So make sure to run multiple random seeds to be sure that you didn't just get a fluke, that when you try a learning rate of 5.0 and it works well, it's not just because you got lucky, but it's actually because 5.0 is a better choice. So don't assume that it works well until you test a few random seeds. But also remember that random seed is not a hyperparameter. So the point is not that you should search for random seeds. The point is that you should try multiple random seeds to validate that the hyperparameters that you chose are actually good hyperparameters. And this is not at all a jab at certain people who are in the habit of doing this. OK, so that's kind of the practical thing, the thing that's good to be aware of as you're designing new algorithms. But then, how can we actually deal with this challenge? It's kind of something that's really profoundly unsatisfying and problematic about this idea that we have to run, dozens of runs of our algorithm just to know if it's working. So we can't, of course, run hyperparameter sweeps in the real world. So if we have real physical systems, if we have a car, an airplane, a robot, I mean, maybe you can if you're lucky enough to have many copies of them. But there's so much variability in the real world that it's generally impractical. So you can run your hyperparameter sweep in simulation, and then try to run the best parameter setting in the real world. But then the question you have to ask is, well, how representative is your simulator? And if from my experience working with lots of simulators, the answer usually is not very. So something is kind of a little problematic here. If you are running a hyperparameter sweep as a kind of integral component of making your algorithm work, then in reality your sample complexity is the time to run your algorithm times the number of hyperparameter sweeps. So your algorithm is in effect a kind of stochastic search plus gradient-based optimization, which is cool, but you have to account for the fact that it's much more expensive in that case. So can we develop more stable algorithms that are less sensitive to hyperparameters? And I think if you're looking for a final project topic and you have some ideas about this, I think that would be an excellent direction to pursue. What can we do? Well, we can think about devising algorithms with more favorable convergence properties. So some of the discussion that John had in regard to trust region policy optimization gets at this idea. There's been some other work on things like adaptive batch size adjustment for policy search methods, things like using statistical significance tests to determine whether you've collected enough samples to be confident that a policy improvement step will actually improve your policy with the return estimate that you can get. So this is some work from Philip Thomas, and there are many other authors that have worked on this. We can look at algorithms that adaptively adjust parameters. So Shishang Gu has this paper called QProp, where he looks at adaptively adjusting the strength of a control variate by testing the degree to which that control variate actually correlates with the returns. So that can be a way to dynamically adjust some hyperparameters instead of having to set them by hand. But in general, there's a lot more research that's needed here. And in particular, I think this is one of those areas where there are a lot of great ideas that have come up in kind of simpler domains, tabular, shallow, if you want to call it that, reinforcement learning. But there's not that much that has been sort of successfully ported over to the world of deep reinforcement learning. So I think there are a lot of excellent research opportunities here. And one caveat that I should say is that, this is devising more stable, more usable reinforcement learning algorithms is not great for beating benchmarks. So in some ways, it's sort of a little bit unsatisfying. But don't be discouraged, because it's actually absolutely essential to actually make RL a viable tool for real-world problems. So I think this is something to think about presenting results. How do you properly illustrate that your algorithm is less sensitive to hyperparameters? But I think it is a really, really important topic. And I think if you're thinking of looking into this, don't be discouraged if you're not beating the benchmarks, because getting that stability and convergence and lack of sensitivity to hyperparameters will pay off in the long run. All right, question.
How stable is A3C?
It's not super stable. Yeah, I can tell you more about that offline. Let's talk about sample complexity a little bit now. So with sample complexity, let's kind of take a step back a little bit and look at some of the algorithms that we've covered and a few that we haven't covered, and actually try to do a little bit of detective work and figure out just how efficient they really are. So these are the algorithms I'm going to discuss on this slide, and I've intentionally ordered them with the most efficient ones at the bottom and the least efficient ones at the top. So as you go up, you use more samples. And I'll tell you about what each of these is. So at the very top, this is actually something we didn't cover in this class, but these are gradient-free algorithms, so algorithms that do not use backprop. There was actually a very nice paper that came out very recently from some folks at OpenAI called Evolution Strategies as a Scalable Alternative to Reinforcement Learning that look at actually applying gradient-free optimization algorithms. In their case, they use something called natural evolution strategy, but other gradient-free algorithms exist like covariance matrix adaptation and so on. Basically, these are methods that try to do a stochastic search directly over neural net parameters without ever having to do backprop. There's some reasons why you might want to do this. These kinds of methods tend to be a lot easier to parallelize. But in this work, they report that these kind of methods are about 10x slower than things like A3C, with runs on Atari numbering about 1 billion steps. So now let's look at A3C. So this is the picture that I showed before, and here this is this task called half cheetah. It's actually a fairly easy Mujoko Gym task, and here we're getting convergence with A3C and a few related methods at about 100 million steps. And we can try to figure out how a policy gradient method like TRPO will do by looking at the OpenAI Gym website. This is a slightly different version of the same task. So this is also half cheetah, but there's some unknown difference because this is a DeepMind internal thing and this is a OpenAI Gym thing. But they're basically the same task. And here we can see very conveniently 10 million. So almost exactly a 10x difference. So this is sample complexity, not necessarily walk log time. So walk log time, this is all parallelized, and this might actually be quicker. But sample complexity, about a 10x drop in samples going from A3C to policy gradient methods like TRPO. Now let's look at TRPO versus methods that use a replay buffer or some other kind of value estimation, like Q-learning, DDPG, or NAF. So for that, we can look at this paper by Gu et al., where they compare to DDPG, that's the green line. And here they're actually reporting number of episodes, but each episode is 1,000 steps. So over here, you can see DDPG gets to a pretty good return and stabilize after 1 million steps. So again, a 10x drop. And in fact, this is about 3 hours of real time. And the NAF experiments kind of confirm that this is 2.5 hours of real time. So kind of almost surprising how close it is, but roughly 3 hours, 2 to 3 hours to learn something meaningful. So again, a 10x drop in sample complexity, going from policy gradient methods that use kind of batch mode learning to these methods that are all kind of Q-learning style that use a replay buffer. DDPG, even though it's kind of an actor-critic method, it really looks a lot like Q-learning because the core of it is estimation of the critic, and then you just propagate gradients from the critic. So you can kind of roughly think of these as all being like Q-learning style methods with a replay buffer. Now, these are all the model-free things. And right around here, this is where we get to like a number that's reasonable for running kind of real physical systems, where you get a few hours of training time. If you go down to model-based methods, now this is actually a different paper. It's actually a different task, but here in this paper, they conveniently ran both DDPG and guided policy search. And this is a log plot, so this is about 10x gap again. So there's again a 10x gap going from these methods to model-based methods. Now here, there's an important caveat to note. It says 20 minutes of experience on a real robot, but that's 20 minutes of experience. It's not necessarily 20 minutes of computation. So once you get to these methods, actually the computation time starts substantially exceeding the experience time. So even if it's 20 minutes of experience, it doesn't mean that training finishes in 20 minutes. You might need another hour or two of computation. Now these are all the deep RL methods. You can actually go even lower. You can look at shallow RL methods like the Pilko algorithm, which I covered at the beginning of this class, which uses a Gaussian process model. Now, Gaussian processes are very data efficient, and unfortunately, it's hard to compare them directly because they work on different tasks. But if you look at some benchmark tasks from the Pilko paper, it's a little hard to see because the font is tiny, but these are basically 1 to 2 minutes of computation. 1 to 2 minutes of experience. The amount of computation is actually substantially more. It's also numbered in the hours. So about a 10x drop for each of these different tiers, with a cutoff for physical stuff right around over here, and this is sort of the non-deep RL thing. Yes?
So how far is the number of steps representative for the amount of data you need? Because, I mean, maybe A3C runs great if you have 10,000 samples, you just repeat them.
So this is, when I say steps, I don't mean gradient steps, I mean simulator steps.
Oh, okay.
Yeah. So steps here means simulator steps, and all these simulators are, I actually adjusted the number of hours or days. That's adjusted based on what the simulator frequency is. So I think on the cheetah task, it's about 100 hertz, and on this one, it's like 20 hertz. So I did the math there properly. It's a little bit sort of abusing the transitive property because like what Pilko does on like a double cart pole is not necessarily representative of what someone else will do on half cheetah. So this shouldn't be taken too seriously, but as a rough kind of back of the envelope estimation, I think this is like a very reasonable way to think about sample complexity. Okay, so we're getting these 10x drops going down from all of the from one tier to the next, but this doesn't quite tell the whole story because this is on relatively simple benchmark tasks. What about more realistic tasks? Well, there is some bad news, which is that we also pay a big cost for dimensionality. So if you look back here and you look at like TRPO and it says, oh, 1.5 days to learn this half cheetah task. 1.5 days doesn't sound that bad. I mean, yeah, it's a long time. It's like 36 hours of having some system running continuously. But if I have to wait 36 hours and get great results, well, maybe that's not a big problem. But that's not the whole story because for the same algorithm, this is the little half cheetah. If you want to run a more complex task like humanoid, now you're getting almost a 10x increase in the number of samples that you need, going from a cheetah, which is, I believe, like roughly 20-dimensional to this thing, which is like in the 50-dimensional range. So the complexity of the task also matters, and it's going to impact the sample complexity a lot. You pay a big cost for trying to use raw images. So these are all operating on low-dimensional, like joint vector, joint angles and velocities. If you switch to raw images, of course, you also need more experience. and you pay a big cost in the presence of real-world diversity. So these tasks are relatively simple in the sense that the agent sees the same thing every time. It's always running on flat ground. It always has the same body, the same joints, the same torque results in the same acceleration. But in the real world, you have a lot of diversity. So no single, no single thing happens twice exactly the same way. If you're interacting with objects, if you're interacting with people, if you're interacting with real-world environments, you get a lot more diversity. And of course, that's going to correspondingly increase the amount of experience that you need to be robust and successful. So I think the stuff on the previous slide is good for understanding the relative sample efficiency of the different methods. But if you're thinking about using deep RL for a real-world task, things get a little tougher because you're probably going to be paying a premium in sample complexity of another 1 or 2 orders of magnitude. Yes?
So one thing that I noticed in contrast to just classical supervised learning is that usually we don't regularize, right? So what would happen if we use some L1 norm to enforce scarcity on our feature space, for example?
Yeah, so there's actually been some work on various ways of regularizing reinforcement learning algorithms, introducing auxiliary objectives, and introducing priors. It does tend to help. So far, I haven't seen any work that produces like an order of magnitude improvement from that. But yes, there's definitely more that you can do there. There is kind of a higher level point that I might make there, which is that oftentimes people use regularization, especially things like sparsity, as a way to get more generalizable features. And in some ways, the way that these RL problems are structured, these two things are in opposition. So this is not, like, the cheetah task is not testing your ability to generalize. It's not testing whether you've discovered a generalizable cheetah gate. It's just testing whether you've overfitted this particular cheetah task. So you might come up with a perfect general regularization and find that your results are much worse. But maybe that suggests that this is not a great way to test for that kind of stuff. Maybe we should have a different evaluation metric, which is something that I'm actually going to talk about in the last little part of this lecture. But first, let me finish up with the challenges of sample complexity. So one of the big challenges of sample complexity for you, a very practical challenge, is that you need to wait a long time for your homework to finish running. But if you try to do this in the real world, then things get even more severe. So real-world learning becomes difficult, or even impractical or impossible, depending on how you want to do it. High sample complexity can preclude the use of expensive or high-fidelity simulators. So, for a lot of little toy exercises, it's fine to use Mujoko. But if you want to solve kind of a more relevant real-world task, you might have a very high-fidelity simulator of your system. Now your sample complexity is going to be a bottleneck, even if you're not directly running on real physical systems. So this is a big limitation in regard to applicability of these methods to real-world problems. And I think it's a really important thing to try to address. What can we do? Well, model-based RL algorithms seem to be really promising. They do seem to be more efficient, but there are a lot of big challenges there. And we can look at designing faster model-free algorithms as well. So here are a few examples of works that have tried to do this. By no means succeeded completely, but made some efforts in this direction. So the QProp paper, again, that I mentioned before, that's a paper that introduced a policy gradient algorithm that has many of the ingredients of Q-learning and replay memory, and actually it's a policy gradient algorithm that runs as fast as value estimation algorithms. There's another paper that you might choose to check out. This is an ICLR paper this year that's a Q-learning algorithm that's much faster on Atari than DQN by introducing some additional actually constraints onto the Q function. And another thing we can do that's maybe a little bit going outside of the bounds of regular reinforcement learning formulations is to bring in prior knowledge, not in the sense of the designer's prior knowledge, but prior data to accelerate reinforcement learning. So there's been some work on what's called meta learning in a reinforcement learning context. This is a paper by Rocky Dwan on actually training recurrent neural networks that can solve reinforcement learning problems faster. And there's an analogous paper from Wong et al. From DeepMind. And then there's this paper by actually one of the course instructors, Chelsea Finn, on also looking at meta learning for reinforcement learning, so training features that allow faster RL by using prior data. All right, so in the last 5 minutes, I'm going to cover the third point, which is scaling up deep RL and generalization. And here I'm going to take a step back a little bit and maybe kind of mention a few things about deep learning that I think are a big part of the reason why people are very excited about it. For example, in a computer vision context, if you look at the kind of problems where deep learning methods have achieved very good results, so that have gotten a lot of attention, a lot of practical applications, and a lot of interest in academia. These are tasks like ImageNet classification that are large-scale tasks that really emphasize diversity and that evaluate primarily on generalization. So the reason that the performance of convolutional neural networks and ImageNet is impressive is not because they can memorize lots of image labels, but because you can train them on a large number of images with labels, and they can actually then label new images. This seems like almost like an obvious kind of, well, not obvious, it is an obvious point to most people who work in computer vision and machine learning, but I think it's an important one to mention here because in contrast, in reinforcement learning, the kind of settings that we're in, if we're learning, let's say, policies for locomotion tasks or Atari or things like that, these are really small-scale tasks that emphasize primarily mastery and are evaluated on performance. So the goal, if you look at a typical kind of learning curve in a deep RL paper, it's not telling you how many things it generalized to, how many different terrains or how many different morphologies of the spider. It's telling you what reward it got. Did it achieve mastery on the task, not did it achieve generalization. So if we're going to seriously think about scaling up deep RL, perhaps one of the first things we should think about is how to move the problem formulation from here up here towards things that emphasize diversity and evaluate on generalization. So where is the generalization? Well, one of the things we can think about is generalizing from massive experience. So can we set up simulated or real-world environments where we can actually train RL algorithms on large, diverse scenes and then test whether they can generalize to new scenes? Just going through that experimental procedure might reveal a lot of weaknesses that we need to address in future research. And we can also look at generalizing for multitask learning. So if we train on multiple tasks, can we actually get policies that effectively generalize to new tasks? Or at least policies that are very good initializations that can then be fine-tuned on new tasks. And this is something that people have looked at in the context, for example, of Atari games. So there's been work on things like policy distillation in this actor mimic paper that look at learning from multiple Atari games to see if new games can be learned more quickly. And of course, the work on meta learning and so forth that looks at training on multiple tasks and then learning new tasks more quickly or generalizing directly to new tasks, and many others. And then the other thing that we can think about when it comes to generalization for multitask learning is whether we can actually have algorithms that set their own tasks for the purpose of future generalization. So the trouble with multitask learning is that someone needs to actually devise those tasks and give those tasks to the algorithm. Can we avoid the need for that by actually having unsupervised or weakly supervised learning of diverse behaviors? And there's been some work on things like training stochastic neural network policies that don't necessarily achieve the best reward on a task, but actually find a diverse set of ways to solve that task for the purpose of future fine-tuning or generalization. So these are some references for that, and there are, of course, many others. OK. Well, I think I'm going to stop there. I have a little bit on reward stuff, but I'll skip that and take any questions that you guys might have. OK. All right. Well, you guys are also welcome to come ask me questions afterwards or in office hours. Please do remember to send your project title and your group members to the homework submission mailing list. And also remember that homework 4 is due soon. There was a little extension that was posted on Piazza, but I believe it's due at the end of the week.